Types of solids. Now we're going to look at two different types of categorizations. First one is going to be the amorphous type. And the second one is going to be a crystalline type. Now we're more focused on the crystalline for this video, but a quick little subset information for the amorphous is that there's no real repeating pattern for this one. So there's no unit cell is what we call it. So no real repeating pattern. I'm going to just put in brackets here, there's no unit cell. Whereas a crystalline structure has a unit cell. So if it has a unit cell, that means it's real and repeating. Also known, maybe we'll put in here in quotation marks, that it's a distinct organized shape. It's another way to think of it. Distinct, okay, and it's organized shape. Whereas an amorphous one, it's indistinct. So you could think of it as kind of disordered. Now, with a crystalline structure, it kind of branches out into these different subcategories. The first one we'll have a look here is a metallic. After that, we'll look at a molecular. And these ones should be quite familiar to you. This one here may not be. This would be a covalent network, and it's different than a covalent bond because molecular are the types of compounds, right? But the types of compounds have these covalent bonds. This is not the type of covalent that we're talking about here. A covalent network is a little bit different. It's stronger than an ionic bond, but they're made out of covalent bonds. And then we'll explain why this network has to do a great deal with that property. And then, of course, we have ionic. We're going to have a small little subset of every single one here and look in detail of which properties preclude for each of these different types over here and provide some examples for each one. Then we will look at some review questions to test your comprehension. Now, as you can see with this picture here, one of them is quite ordered, and this one looks quite disordered over here. So it's quite easy to tell that this one over here is going to be known as the amorphous structure. And this one here is going to be the crystalline structure. Let's look at the crystalline one. So for the crystalline structure, let's first look at the first subcategory of a metallic bond. For metallics, the electrons are not stuck in the bonds. So they're not stuck in any covalent bond or ionic bond. They're not stuck in any directional bond. They're quite free-flowing in a way. So maybe I'll put here in brackets, they're free-flowing. What else we could add here is, again, there are no directional bonds. So they're not in a segmented little bubble where they're not able to escape. They are actually free-reigning. They can go anywhere they want. They're not bound to a specific ion. They can actually bounce from any atom and then share those electrons with everyone. So no directional bonds. And I guess I can write here, this is why they're kind of malleable. That's why metals are malleable. They're not brittle in a way. And then we'll have, lastly, we'll write here, they can take the stress. Can take the stress of changing shape. Okay, again, because they don't have these directional bonds, when this breaks, it's not going to break apart into like a powdery or brittle formation. It's actually going to just take the shape, hence why we have deemed it as malleable. So let's have a look at a couple of examples here. A few examples here. Let's say, iron. This is obviously a metal, and then we have something like steel. Now, steel is more so, it's like an alloy. So it's a combination of iron and carbon. And we also have Pb and maybe like cobalt. So these are examples of these metals. What we also maybe want to add here as a star, these are all relatively ordered. Ordered array of electrons. You may think that they're disordered at first, but disordered are only the amorphous ones. The amorphous ones have no real relative pattern and quite disordered. Crystalline is more ordered. So despite the metallic ones being thought of as disordered, it's not up to that extent. It's still within a crystalline structure, meaning that it has a revealing pattern, but not disordered, just ordered. It's just that the electrons can just kind of go everywhere in a free range formation. Now let's have a look at molecular. In moleculars, the electrons are stuck in the covalent bonds. And because they're stuck in these covalent bonds, this means, I'll put in brackets here, that they're not free to move. They are confined within that segment of that bubble of that covalent bond, not free to move. What we can also know is that it doesn't take much energy, to separate the molecules. Now, not in this video, but another video that I'll be putting out, we're going to be looking at the different types of the intermolecular forces and talk about how, London dispersion, dipole-dipole, hydrogen bonding, how they all play into effect. Obviously, near the ones that are higher up of strength are going to be able to separate molecules quite easily. So let's say ion dipole or, hydrogen bonding. But for something like a molecular one, it doesn't require much energy. So the ones that have like London dispersion force or dipole-dipole, they're enough to even separate these molecules. So in a molecular, it doesn't require much energy to separate them, so it's quite weak. They're weakly bonded. Now, the last thing I want to put here as a star is that you can actually tell where one piece starts and where the other piece ends. So if I were to maybe draw a little illustration here, I'm just going to kind of make them on different shapes. And as you can see, there are clear distinctions here, maybe here and here, this one and this one, right? Both of these. There's a distinction between here, a distinction between there, a distinction between this and this medium, this one and this medium, right? It's quite easy to tell that they are separating from one piece to the next. So maybe I'm going to write here is that you can tell where one piece starts and the other piece ends. This is quite in stark contrast to a covalent network where you will not be able to tell where one piece starts and one piece ends. It's actually quite one big sheet, and we're going to be looking at that next. Next, in a covalent network, it is one huge molecule. I'm just going to preface this at the beginning. the question with an exclamation mark. It is one huge molecule. So what do I mean by that? This means that there is a giant macromolecule, but there is a giant aspect of no beginning or end. Now don't take it literally, but it's quite difficult to figure out where this beginning or end is. So in the previous example where we looked at a molecular structure, it's easy to tell where they are beginning and where they are ending. Okay, all of these boundaries here are quite easy to tell where one starts and then where one ends over here, and then it starts here and then ends here and then starts here and then ends here, etc. In a covalent network, we're not able to tell. It's just one large sheet, okay? Because it's one large sheet, there's a specific name for it. Like I said, it is a large unit cell sheet. And this large unit cell sheet is a macromolecule. It's quite difficult to break apart. But if it does break apart, I'll put in stars here, if it does break apart, if broken, ... it's not the actual intramolecular bonds. It's not the intramolecular bonds themselves that break. But rather, it's the entire shell sheet. That breaks. Again, these intramolecular bonds, so that's like, ionic, covalent, etc. Right? These are the intramolecular bonds. Intra means within the molecule, not between molecule and molecule. It's within the molecule. It's not those that are breaking, but it's the entire cell sheet that breaks. So it's hard to tell where here it actually breaks. Maybe the whole segment in that area that's broken. Okay, so this is why they're very, very strongly held together, because it's a large aspect, large surface area that all of these bonds within the boundaries are taking place to kind of keep them nice and stuck together very, very strongly. Now let's have a look at a couple of examples. Let's have a look at maybe diamond, and let's say graphite. Again, these are some allotropes over here. It's just carbons, right, that are just keep going and going and going and going. And then we have maybe like silicon dioxide, and then let's say like silicon carbide. So for example here, these are known as the allotropes. Okay, and then these allotropes, for example, are the carbons that just keeps going. The carbons that just keeps going. And in the previous video, I've already told you that, carbon, it's not just its nature to bond with just two for those orbitals to overlap. It likes to bond 4 times, right? 4 directional tetrahedral bonds. So because it's 4, it's very well balanced, very even in terms of equilibrium. And again, these tetrahedral bonds are quite strong, so it just keeps going, going, going. And whenever, like let's say diamond has lots and lots of carbons bonded together, it just keeps going. So it's very, very difficult to find where it actually broke. And because it can't, we look at the entire cell sheet, which is why it breaks in that regard. Same thing with graphite. Okay, it's a multitude of these carbons that are arranged in a way where these directional tetrahedral bonds are spread out. So this entire cell sheet is very glued well together. And for any graphite that's going to be broken off, you're looking at the entire cell sheet that breaks, not the intramolecular bonds. Next, let's look at the ionic. Okay, I'm going to also add here the crystal, because in ionic bonds we creating crystal lattice. Now, what is this crystal lattice? It's just when you have a cation and an anion. So an ion here that's positive, and then an anion here that's negative. This cation and anion, these are electrostatically very, very attracted to each other. This creates crystal lattice. Now, it's not a perfect crystal. If it was a perfect crystal, then we would have to look at the third law of thermodynamics. We're not going to get into that, approaching pretty much absolute zero, where it's a perfect crystal where there's no longer any more disorder occurring. But we're not talking about that kind of crystal, right? This crystal obviously is going to have a lot of these vibrations within these particles still going on. So in layman's terms, it's a crystal lattice, not, very, very specific. But we're not going to go into that much depth. Just know that it's a crystal lattice, and the lattice just means they can't move. Now, don't take it literally of not moving. They're obviously still going to be vibrating. But just in general layman's terms, we'll say they can't move. So lattice means that they cannot move. This means if we have, let's say, an example of Na plus Cl, 1 minus Na plus, let's do Cl 1 minus down here, Na plus Cl 1 minus. So as written here, you can't move electrons. Can't move electrons. Okay, so the electrons here will not be able to move around to, let's say, this one here, or this one here, or this one here, because they're not in a molten state. So maybe I'll write here, can't move electrons unless in a molten state. If we have another way, like hydrogen bonding, for example, this could work and break them apart, because hydrogen bonds are very, very powerful. So if again, these are positive ends, and this is a negative end, and if oxygen wants to take this sodium apart, it can, because even though these are held strongly together, the H2O is still able to dissolve this. If there was another salt that prefers one another more than the actual water, then it won't dissolve in the water. But in this case, they don't prefer each other as strongly, so the water is strong enough to take this Na+, this cation, apart quite easily, actually. Now, a few examples of an ionic crystal could be, let's say, CaCO3. Quite easy to tell. Ca here is a positive charge, the cation. CO3, 2 minus here would be the anion. These charges cross over, you end up just getting CaCO3, so that's what that is. Or we have, let's say, we've already written it here, so might as well do that too. NaCl, again, Na was the cation, chlorine was the anion. These are their respective charges, so you just bring them, you just cross them over, cross this one over, same deal. You end up getting NaCl11, and you can just deem it as that as the final answer. So CaCO3 and NaCl are some examples of these ionics, again, between a cation and an anion. Now let's have a look at some allotropes. Now looking at allotropes, we've already kind of looked at it a little bit with the diamond and graphite, but just a formal definition here, they're just different orientations. Of carbon, specifically carbon. Okay, so all of them are networkly covalent. Now let's have a look at, diamond, because that's the one we used in the previous example. So in a diamond, you should have already known that the carbon should have a tetrahedral shape, so we should have 4sp3. If you're kind of confused about what 4sp3 is, please look at the previous video. So sp3, the previous video was about hybridization. So the central carbon here does this, and then all of the valence electrons are spread out this way, as such. Okay, so this is what's happening with a diamond. Another example is, let's say, the graphite. The graphite does the same thing as well. Okay, but the graphite, instead of tetrahedral shape, it's going to be more trigonal planar. So if we have something like that, okay, then we have our sp2s, because we need 3 sp2s. We have these 3 electrons written here. Each unit cell is a macromolecule, remember that. So when you have a graphite here, like in a pencil, and it breaks apart, you're not actually breaking the intramolecular bond, like we discussed earlier. You're breaking the actual whole unit cell as a whole. So if we look, let's say, at this one over here, again, it's rearranged this way in 3 different segments, this segment, this segment, this segment. So if we have another carbon down here, and let's say there's a double bond in that direction, single bond in this direction, and then now you have another carbon here with a single bond and another double bond, and another carbon here with a single bond and a double bond here. If we look at the types of bonds, so if this was a sigma bond here, and let's say this was a pi bond, and let's say this one here was like a pi bond and this was a sigma bond, or this one was a sigma bond and this was a pi bond, we don't know where the malleable pi bonds are. So because we don't know where the malleable pi bonds are, this could be a resonance structure. So these pi bonds, so these pi electrons, they're delocalized. So this one over here, this one over here, this one over here, they are delocalized. So because they're delocalized, the pi bonds orbit, okay? These pi bond orbits of one sheet can overlap to another sheet. So this pi bond here can overlap to another sheet. Okay? Or this pi bond here can overlap to another sheet of carbon. Or this pi bond here can overlap to another sheet. So the pi bonds overlap one sheet over the next to make one large area of delocalized electrons. Because these electrons can overlap these pi bonds. This is why the pi bonds are not as strong. If you look on the previous video of hybridization, we briefly looked at the pi bonds not being very powerful. It's the sigma bonds that are the strong ones that do a direct crossover. Because these do not do a direct crossover, it's not going to be as strong. And if I were to kind of show you on the pi bonds, I looked at it very, very briefly in the last video, but they're on either side. So this pi bond over here that we see here, that I'm going to be highlighting in green, it's on both sides. And again, I've already mentioned this, but the electron densities in the previous video prove this. Okay, they're on both sides. Same thing here. This pi bond over here, it's not as simple as that. It's on either side. So these pi bonds that are able to transmit these electrons through give it this delocalized sense of conductivity. So even though these are networkally covalently bonded, so very tightly bonded, because they're all part of just one unit shell. If you break, you're not able to break these. You have to break the whole thing. Again, we don't know where it's going to break. These electrons are able to conduct electricity or heat. So diamonds, for example, have quite high thermal conductivity. They conduct quite well. Again, even though they are directionally bonded, they can still allow these electrons to go from one end to the next because these pi orbitals overlap other pi orbitals of one another. If we look here specifically, this was what I was talking about. The pi bonds are organized in such a fashion, one on top and then one below. And these are the review questions that I want you to look at. let's have a look at each one. Name and describe the general types of chemical bonding and identify what these different types of bonds have in common. Number 2, what happens when metal atoms interact with metals of the same or different metals and why. And lastly here, we're kind of looking at thermal conductivity, so how well it conducts heat. For example here, metals here, again, it's quite obvious they're the best conductors. They have a thermal conductivity of 400 watts per meter Kelvin. That's the unit of measurement. Okay, just look at these values, the numbers that are more important. So 400, quite large, but we look at something like wood, which is covalently bonded, right? It's a molecular compound, organic, doesn't have metals. They're all non-metals. So as you can see here, it's 0.5, quite a small number. But we look at diamond, also made mostly out of carbon. However, is 2,000, so it's a very, very large number. Diamonds being covalently bonded, how do they have such a high conductivity? They don't have metals, so how is it so high conductivity to heat? Now, this here might be a little bit tricky. You have to tap into the material that you might have already learned back in your previous grades. It's not just about what we looked at today in this video. You might also have to look at the amount of charge that is in play as well, and charge mobility if you've maybe learned that. If not, try your best, but I'm going to be giving you the solution anyway. When you do this, please make sure that you pause this video right now, try your best, and then look at the answers after you have completed them on your own to the best of your ability, to the best of your degree. This is the answer for the first question. This is the answer for the second question. This is the answer for the third question.